So this video is for sections 2.5 to 2.8 in the book. I really encourage you to read through the book. It is really helpful supplemental material in addition to this video. In this video today, we're going to calculate unit vectors, which we already talked about some in class before. We're going to develop an understanding of the need for and application of unit vectors, and then we're going to understand 3D resultant forces and angles. So some of this should be reviewed from some of your math classes, but basically, so the 2D position vectors, I'm going to draw this up. Let's see. So if we have the position vector AB, so that's R AB, it can also be written as R of B with respect to A. So AB is from A to B, and B slash A is of B with respect to A. So those are saying the same things. Basically for this one, let's say that A is 1x and 3y, 1, 2, 3. So that's A, and that's 0.1, comma 3. This is x and y. And then it's going to B, which is 5, 6. 1, 2, 3, 4, 5. So it's 5, and 1, 2, 3, 4, 5, 6. So that's B, and that's 0.5, comma 6. And it's going from A to B. So R of AB, that vector, is going to equal 4i. So we need to go over. So you're going to think about how many do we need to go in the x direction to get over to the b. So to go from 1 to 5, so it'd be 5 minus 1, which is 4i. You can check that by starting at a and going, okay, 1, 2, 3, 4. So that gets us over that line. And then we need to go up 1, 2, 3 plus 3j. You could also do that 6 minus 3 to check that. So the position vector is a fixed vector which locates a point in space relative to another point. So that's A from A to B, or of B with respect to A. The magnitude of that, so the magnitude of R, A, B, would just equal the square root of 4 squared plus 3 squared. And that's one of those common triangles, so we know 3, 4, 5, so we could just say 5 is that magnitude of A, B. So that should be a review. To just extend that, the equation, so this is just the general equation to calculate the position vector. This is RAB equals XB minus XA I plus YB minus YA J plus ZB minus ZA K. So that's just what we just did. It's just the generic version. The basic equation for the general equation for the magnitude of the position vector is that magnitude of RAB that equals the square root of basically each of those components squared. So XB minus XA squared plus YB minus YA squared plus ZB minus ZA squared. And then the unit vector, which we talked about in class, so the Cartesian unit vector. This is UA equals A, so that vector over the magnitude of A. And remember with that, the magnitude is 1, it's dimensionless, it doesn't have any units, and it points in the same direction as the original vector. So this just tells us that direction. So vectors have magnitude and direction. The unit vector only tells us direction. So the magnitude is 1, dimensionless, and points in the same direction as original vector A. So that just tells us direction. So now we're going to get some into the 3D vectors. So 3D vectors. These really aren't too hard. You just need to understand and sort of be careful with them. Sometimes they can get kind of big as we're dealing with them. But basically with this, we have two different ways of looking at these. So there are coordinate direction angles and then transverse and azimuth angles. So we're going to start with the coordinate direction angles. And basically with this, and we'll see how my drawing goes with it, basically with this we have y, x, z, we have a vector A, and we have the angles that we're interested in is the angle from A up to that z axis, and that's gamma, the angle down to the y-axis, which is beta, and then the angle to the x-axis, which is alpha. And these angles are between the vector and the positive x, y, or z axis. So you see with the gamma, it goes from A up to the z-axis, to the positive z-axis. So that means the range of those is between 0 and 180 degrees. Using trig, we can sort of figure out these relationships, and I'm just going to write them down for you. But so the cosine of alpha equals, so that's the cosine of this one. Cosine is adjacent over hypotenuse, so that would be that AX over A. Cosine of beta equals, this one is a little bit easier to see just because of where it is. So cosine SOHCAHTOA, cosine is adjacent. So cosine of beta equals that adjacent, so that's that AX over that hypotenuse, which is A. So that's I said AX, AY. So that Y component of that A vector over A, and then cosine of gamma equals AZ over A. And so you can see that one over here, that if we take that Z component of the A force, that's AZ. So cosine of that angle would equal that AZ over A. So that's adjacent over hypotenuse. Make sure you understand that. And then an important relationship is that cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. Sometimes that'll be the fourth equation that you can get to. And then the unit vector, So UA equals A over the magnitude of A. And so we can figure that out. So A is AXI plus AYJ plus AZK. And we need to divide it by that magnitude of A. So divided by A, and divided by A. Or you could say the unit vector of A equals cosine alpha I plus cosine beta J plus cosine gamma K. So if that's the unit vector there, then we also would know that the vector A is going to equal that magnitude of A times UA. And so that vector A is going to equal A cosine alpha I plus A cosine beta J plus A cosine gamma K. And then once you have these all in Cartesian vectors, so in this I, J, and K, then it's pretty easy to add them. So say you had a vector A and a vector B, you could just do the resultant vector. So R equals A plus B, and that would be that AX plus BX in the I direction plus AY plus BY in the J direction plus AZ plus BZ in the K direction. So that makes it pretty easy. Next, the other important thing that the book uses, sometimes you deal with transverse and azimuth angles. So for these, do a quick drawing. Y, Z, X. We have our A vector. Make it look similar to the other one. And then for this, we have this angle phi. And then if we take A down to this XY axis, see, this is A prime now. Then we have this angle of theta. And so with these, what's important, and you can figure these out just by looking at it, so take a little time to make sure this makes sense to you. AZ, so we're interested in that Z component of the A, so we're interested in this right here, is the AZ. So AZ is going to equal A cosine of phi. So cosine is the adjacent, so that gives us that. AX is going to equal A times the sine of that phi, so that's going to give us this right here, which is translated down to, it's translated down, and then times that down to this one, and then the cosine of theta to get us over to that A sub x. So make sure that makes sense to you. I don't know that I explained it that well. A times sine of phi, so that gets us down to this A prime, and then times cosine of theta. The book explains it a little different. You may want to look at that. And then AY equals A, that same sine of phi, so we're getting down to that A prime, A sine of phi. And now we want to get that, sort of this component is the AY, which would also be here. So that would be sine of that theta, because it's the opposite, SOHCAHTOA. So This gets a little bit more complicated with the 3Ds. I really recommend that you look through the book and make sure you have a good understanding of it. But with that, I think we've hit our learning objectives. We calculated unit vectors, did a little review of that, talked about some of the need and application of unit vectors. They tell us position, tell us direction of the vectors, and then understand 3D forces, resultant forces, and angles. And I recommend that you look at the book, sections 2.5 to 2.8. Thanks.